Hello students, welcome back to the session. There is scattering of light. So basically let us see what do you mean by the scattering of light. So scattering of light is an optical phenomena basically. It is an optical phenomena. So it means that it is concerned to light. Okay. So what happens whenever whenever any light which is traveling through the medium. Okay. So whenever the light is traveling through the medium, and if there is a deviation in the path of the incident light, there is a direction of the incident light, then that will be known as a scattering of light. So scattering of light, we can say it as, or we can define it as, it is an optical phenomena where whenever the light travels through the medium, so due to the presence of the particle in the medium, so there is a deviation or there is a change in the direction of the incident light. So this will be known as the optical phenomena that is known as the scattering of light. So basically scattering of light is nothing but as we said, there is a deviation in the direction of the incident light, that is called as scattering of light. So on what basis does this scattering of light depends? So one of the major factor, it is nothing but the wavelength of the incident light. So it mainly depends on the wavelength of incident light. And second point on which the scattering of light depends is the size of the particle. Remember students, the scattering of light will mainly depends on the two factors. The first factor is it depends on the wavelength of the incident light. I have written the symbol wavelength of the incident light, and it also depends on the size of the particle that is present in the medium. So on these two factors we have the dependency of the scattering of light. See, whenever any light travels through a medium, so there is loss of energy for the light in two ways. First one is absorption. So due to absorption of light by the medium, there is a loss of energy, and second one is due to scattering. Okay, so whenever any light ray passes through any medium, so there will be a loss of energy. Okay, so the first source of loss of energy for the light ray is due to the absorption, and the second one is scattering. See, in case of absorption of light, okay, so the energy of the light ray or the light will be absorbed by the medium. So absolutely what happens, there is an increase in the temperature. So whenever the medium, there is a particles of the medium absorb the light energy, so definitely there will be an increase in the temperature. So when our temperature increases, according to kinetic theory of gases, certainly there will be an increase in the speed of the molecules, right? That is the VRMS changes. So as the temperature, it is a temperature dependent, so therefore the velocity is directly proportional to square root of the temperature. So therefore the speed of the molecules will also increase. Okay, if I naught is the intensity of incident light, and if I is the intensity of the scattered light, then the relation between the original intensity or the intensity of the incident light and the intensity of the scattered light is given by I is equal to I naught e to the power of minus alpha into t, where alpha is nothing but known as the absorption coefficient. And t is the thickness of the medium. Okay, now in case of scattering, the energy of the incident light is absorbed and it will be re-emitted by the particles of the medium. That therefore this is what we call as the scattering of light. There is another definition for scattering of light, is nothing but the absorption and re-emission of the radiation by the particles of the medium is known as scattering of light. So the another definition for scattering of light is the absorption and re-emission of light by the particles of the medium is known as scattering of light. Okay, so there will be two simple definitions. One is it is an optical phenomena in which the light, whenever it enters any medium, okay, so if there is a deviation or change in the direction of the incident light, then that is an example for that is a definition for scattering of light. Or another definition for scattering of light is the absorption and re-emission of the light by the particles of the medium. So that will be the another definition for the scattering of light. So now types of scattering. So there are two types of scattering. One is known as coherent scattering and the other is incoherent scattering. One is coherent scattering and the other is the incoherent scattering. As we all know that coherent means it is same, incoherent means it will be different. So what is changing and what is not changing means, in case of coherent scattering, the wavelength of the incident light will be same or it will be equal to the wavelength of the scattered light. So this type of scattering will be known as the coherent. Coherent means same. So what is same here? The wavelength of the incident light and the wavelength of the scattered light is one and the same. So therefore such a type of scattering is known as coherent scattering. So example for coherent scattering is Rayleigh scattering and second one is Tyndall scattering. So the example for coherent scattering, one is Rayleigh scattering and the other will be the Tyndall scattering. So what do you mean by incoherent scattering? So if the wavelength of the incident light, if it is not equal to the wavelength of the scattered light, or if the wavelength of the scattered light is not equal to the wavelength of the incident light, then such an scattering will be known as incoherent scattering. Now example for incoherent scattering is Raman scattering, which we will be dealing later in the next video. So we will be dealing with incoherent scattering, that is Raman scattering. So if the wavelength of the scattered light is not same as that of the wavelength of the incident light, then such a type of scattering will be known as incoherent scattering. And the example for incoherent scattering is Raman scattering. Just now we are discussing about that is coherent scattering. And the examples for coherent scattering is Rayleigh scattering and Tyndall scattering. So what is the important factor on which the scattering of light depends? That is, it depends on the one is wavelength and the other is size of the particle. So these are the two factors on which the scattering will depend. So if the size of the scattering particle is less than, okay, if the size of the scattering particle A is less than the wavelength of the incident light, then there is a possibility of Rayleigh scattering taking place. Understood, students? See, here what we are discussing means we are discussing about coherent scattering. In coherent scattering means if the wavelength of the scattered light is same as that of the wavelength of the incident light, then such a scattering will be known as coherent scattering. The two examples for coherent scattering is one is Rayleigh scattering and the other is the Tyndall scattering. See, scattering mainly depends on two factors. One is the wavelength of the incident light, and the other is the size of the particle. So now if I consider there is A is the size of the particle, and if the size of the particle is less than the wavelength of the light, then Rayleigh scattering is most likely to take place. In Rayleigh scattering, different colors will be scattered by different amounts. So in this, there is, in case of Rayleigh scattering, different colors of light will be scattered by different amount. So therefore, violet is the most scattered color, and red is least scattered color. Remember students, in case of Rayleigh scattering, violet is the most scattered color and red is the least scattered color. And in case of Rayleigh scattering, the intensity of the scattered light is always inversely proportional to the fourth power of the wavelength of the light used. Remember, these points are very important. Okay, so in case of Rayleigh scattering, the wavelength, there is different colors or different wavelengths will be scattered by different amounts. The intensity of the scattered light will be always inversely proportional to the fourth power of the wavelength of the light used. So since red is having greater wavelength, so therefore greater wavelength means less intensity, that is it is scattered less. Okay, that is the wavelength of this, intensity of the scattered light is less. So violet is having lesser intensity, so therefore it will be with lesser wavelength it will be having more scattering. Okay, so therefore violet will be the least violet is the most scattered color and red is the least scattered color. Now let us see what do you mean by Tyndall scattering. See here what happened. If the size of the scattering particle is less than the wavelength of the light used for the scattering, then the most probably Rayleigh scattering will be taking place. If the size of the scattering particle is approximately equal to the size of the wavelength of if the size of the scattering particle is comparable or equal to the wavelength of the incident light, then the type of scattering that might take place is Tyndall scattering. Or if the size of the scattering particle is comparable or equal to wavelength of the incident light, then Tyndall scattering will takes place. So example for Tyndall scattering is, that is scattering of light by smoke. Okay, so this is an example for Tyndall scattering, and the example for Rayleigh scattering is, there is blue color of sky, and sun appears red during sunset and sunrise. Okay, so this is the example for Rayleigh scattering. So why does the sky appears blue? Okay, there is one reason where there is an example for Rayleigh scattering. That is the reason for blue color of the sky is explained on the basis of Rayleigh scattering, and the sun appears red during sunset and sunrise. So this also can be explained on the basis of Rayleigh scattering itself. Now let us see, why does the sky appear blue? That is blue color of sky. See, in case of Rayleigh scattering, the most scattered color is violet, as we discussed in the here it is violet is the most scattered color and red is the least scattered color. So even though violet is the least scattered color, our eye is sensitive to blue color. Remember students, in case of Rayleigh scattering, we discussed it just now, that is blue color, that is violet is the most scattered color, and here we can see that violet is not that much sensitive to our eye, so therefore blue color, that is blue color, is sensitive to our eyes, so therefore the sky appears blue. Why? Because see, when we look at the sky, we receive the most scattered color, that is violet. So since violet is not that much sensitive to our eye, so therefore it is the blue color of this blue color that we receive at our eye, so therefore the sky appears blue. Okay, and similarly, if you see the sea water, it also appears blue. Why? Because we are seeing the reflection of the skylight, so therefore to some extent the sea also appears blue due to the Rayleigh scattering. So now let us see why is the sun appear red during sunset and sunrise. See, we all know that the shape of the earth is not exactly spherical, it is little bit geoid shape like this. Okay, so during the sunrise, this is the east, let us consider, and this as the west. So during the sunrise or sunset, okay, so if you are, the person is standing here and looking, okay, so it has to travel a longer distance during sunset and sunrise. So since the sunlight has to travel a longer distance due to the geoid shape of earth, so at the point of receiving, okay, by any person, so it is the that is the least scattered color that we receive. So the least scattered color according to Rayleigh scattering is red, so therefore during sunset and sunrise the sun appears red due to the Rayleigh scattering. Now let us continue with incoherent scattering. So what do you mean by incoherent scattering? It is nothing but a type of scattering in which the wavelength of the scattered light is not same as that of the wavelength of the incident light. Okay, so what do you mean by incoherent scattering? Means it is a type of scattering in which the wavelength of the scattered light is not equal or not same as that of the wavelength of the incident light, and the example was Raman scattering, which is also known as Raman effect. So this effect was discovered by our Indian scientist, the proud scientist of India, that is Sir C.V. Raman, hence the name Raman effect. So now let us see what do you mean by Raman effect. Okay, see, whenever we have any monochromatic source of light, so the definition for Raman effect can be explained with the help of a small diagram. So here is our diagram. See, the definition for Raman scattering is as follows. Whenever any monochromatic light is made to pass through any organic liquids such as benzene and toluene, the scattered light, if it is observed in a direction perpendicular to the direction of the incident light, then the scattered light consists of an additional frequencies than that of the incident light. Incident light was present, along with this incident light there were other frequencies other than that of the incident lines, which are, some lines were having greater frequencies and some were having lower frequencies. So this effect is what we called as the Raman effect. I'll repeat once again. So whenever any monochromatic light is made to pass through any organic liquids like benzene and toluene, and if this scattered light, if it is observed in a direction perpendicular to the direction of the incident light, then the resultant spectrum consists of other frequencies or additional frequencies with that of the incident light. Okay, so this type of scattering is what we called as the Raman scattering. Okay, definition for Raman effect is as follows, that is, whenever a beam of, or whenever a monochromatic light is made to pass through any organic liquids, that is any liquids, that is organic liquids like benzene or toluene, and if the scattered light is observed perpendicular to the direction of incident light, the scattered light consists of additional frequency along with the incident light. So this type of scattering, or this is what we call it as Raman effect. So the additional frequency spectral lines that we get are known as Raman lines. That is, those spectral lines with additional frequencies other than that of the incident light. So those lines are called as Raman lines. Okay. Now, and the spectrum will be called as the Raman spectrum, and this total effect is known as Raman effect. So if nu L is the frequency, nu I is the frequency of the incident radiation, and if nu S is the frequency of the scattered radiation, then the change in the frequency of the scattered radiation and the incident radiation can be written as nu I minus nu S. Nu I is the frequency of the incident light and nu S is the frequency of the scattered light. Now delta nu can be written as frequency of the incident light minus frequency of the scattered light. This delta nu is known as Raman shift. Remember this, we'll be calculating or will be in need of this equation during our numerical problems. There are a few features about Raman spectrum. There is Raman spectrum or Raman shift is different for different substance. Remember students, these are the small important points that where your concept problems comes. Raman shift is different for different substances, and Raman shift is independent of the frequency of the incident light. That is what the shift you have calculated. This shift is independent of frequency of the incident light. Remember once again. So the Raman shift delta nu, it will be independent of the frequency of the incident light. So those lines which are having, that is, if delta nu is positive, it means that the frequency of the incident light is greater than the frequency of the scattered light. So such lines are called as Stokes lines. Remember once again, we know that delta nu is nothing but known as the Raman shift. Raman shift is written as nu I minus nu S, or nu I difference, okay, difference nu S. If delta nu is to be positive, it means that is here delta nu must be positive, means nu I should be greater than that of nu S. So therefore frequency of the incident light will be greater than that of the frequency of the scattered light. So such spectral lines are called as Stokes lines. If delta nu is negative, then the frequency of the incident light will be less than that of the frequency of the scattered light. These type of spectral lines are called as anti-Stokes lines. Delta nu Raman shift is to be negative, means then according to this equation, nu I must be less than nu S. That is, frequency of the incident light must be less than that of the frequency of the scattered light. Then such a type of spectral lines that we get will be known as anti-Stokes lines. If you indicate the same thing in terms of wavelength, see, frequency and wavelength are inversely proportional, we know that. See, in case of Stokes lines, okay, what happens? Frequency of the incident light is greater than that of the frequency of the Stokes lines. In terms of wavelength, it will be ulta, that is means it will be vice versa, that is the wavelength of the incident light is less than the wavelength of the scattered light. Remember students, once again, frequency of the incident light is greater than the frequency of the scattered lines, means then we call such a spectral lines as Stokes lines. In terms of wavelength, if you are writing, since frequency and wavelength are inversely proportional, okay, so here we have greater that is frequency of incident light is greater than frequency of the scattered light. Here it should be reverse, that is, if the wavelength of the incident light is less than that of the wavelength of the scattered light, then such a Stokes lines are called as such a lines are called as Stokes lines. Or we can directly say that Stokes lines have longer wavelength than that of the incident light. Remember, there is the wavelength of Stokes lines is longer than that of the wavelength of the scattered light. Similarly, for anti-Stokes lines, we know that the frequency of the incident light is less than the frequency of the scattered light. That is, if that is in terms of wavelength, frequency of the incident light will be greater than that of the wavelength of the scattered light. So therefore, for anti-Stokes lines, it will be having smaller wavelength than that of the incident light. Okay. So this is about Stokes lines and anti-Stokes lines. Let us recall once again. See, what do you mean by Raman spectrum? The resultant spectral lines which are obtained due to Raman scattering is called as Raman lines. If nu I is the frequency of the incident light and nu S is the frequency of the scattered light, then Raman shift can be written as nu I difference nu S. So Raman shift is different for different substances, and Raman shift is independent of the frequency of the incident light. Now, if delta nu is positive, it means that nu I must be greater than nu S. So then those spectral lines obtained in case of Raman spectrum is called as Stokes lines. And if delta nu is negative, it means that frequency of the incident light will be less than that of the frequency of the scattered light. Then such a spectral lines that are obtained is called as anti-Stokes lines. Now if you need to write in terms of wavelength, for Stokes lines, you can see that the frequency of the incident light is greater than the frequency of the scattered light. So therefore the wavelength of the incident light will be less than the wavelength of the scattered light. So therefore we can say that in general Stokes lines have longer wavelength than that of the wavelength of the incident light. So if we come for anti-Stokes lines, we can see that frequency of the incident light will be less than the frequency of the scattered light. So obviously the wavelength of the incident light will be greater than that of the wavelength of the scattered light. Now, so for anti-Stokes lines, we can see that these anti-Stokes lines will be having a smaller wavelength than that of the incident light. So let us see the experimental arrangement of Raman effect. The experimental arrangement for the Raman effect consists of the following parts, which is shown in the diagram. It consists of a glass tube AB, okay, which is filled with a dust-free benzene liquid. At one end there is an window, there is W attached to it, to the glass tube, and we have a other end, we have an horn shape, other end will be drawn into an horn shape H, and it is blackened, and we have an water jacket which comes in and comes out. There is the water will be coming in, and at the other end it will be coming out, and it is surrounded by a reflector. So there is R is a reflector, and we have a mercury arc lamp. Okay, so when it is switched on to this filter, light will be entering into this liquid, that is a glass tube which is containing the benzene liquid. The filter allows only 4358 blue light to get into this glass tube which is containing a benzene liquid. The scattered radiation which is coming out, so is observed in a direction perpendicular to the direction of the incident light, so and that can be photographed with this setup. So here we have the two collimated slit, and here we have the travelling microscope where we can get focused into the spectrum which is observed in direction perpendicular to the direction of the incident light, and the spectrum can be developed, and on developing the photographic plate we can see the various Stokes and anti-Stokes lines. So after studying the experimental arrangement of Raman effect, now we shall see about the quantum theory of Raman effect. So there is classical theory fails to explain the existence of Stokes and anti-Stokes lines. So therefore, with the help of quantum theory, we will be studying the how there is an existence of Raman lines, that is Stokes lines and anti-Stokes lines. So according to quantum theory of light, okay, so let nu be the frequency of incident light, and we all know that light consists of small packets of energy, that is what we call it as photon, and the energy of each photon is given by h into nu. So whenever this photon is incident on solid, liquid or gas, the photon will interact with the molecules which are present inside this substance. So now if you consider this in case of elastic collision, so we all know that elastic collision, there is no change in the energy. So therefore, since there is no transfer of energy from the photon to the molecule, so the photon is scattered without any change in the energy, and the frequency of the scattered photon is same as that of the incident light. This will be that is, from this we can explain the unmodified line in the Raman spectrum. Okay, so if we consider the inelastic collision, if you consider the inelastic collision, so for this let us consider a molecule of mass m, that is the scattering molecule, that is it can be written as mass of scattering molecule, mass of the scattering molecule, and this scattering molecule is in the energy state, or let us consider E1 is the ground state energy, that is the E1 is the energy of the scattering molecule. Now it is nothing but this energy is nothing but the sum of the vibrational, rotational and electronic energy levels. Now let us consider this molecule is moving with a velocity v1. Okay, now when a photon of energy h into nu1 is incident, and this photon will collide with the scattering molecule. Okay, now what happens after absorbing certain energy, this molecule will go to the higher energy state E2, okay, and the photon is scattered with a frequency which is equal to nu2, and the particle, that is a molecule, will move with the velocity v2. Okay, now the molecule will start moving with the velocity v2. So according to law of conservation of energy, we have E1, that is E1 is nothing but the energy of the scattering molecule before absorbing the photon, which is nothing but the sum of vibrational energy, rotational energy and electronic energy levels, and half mv1 square, so that is nothing but the kinetic energy of the molecule, and h into nu1, where nu1 is the frequency of the incident light, and this was equal to the energy state of the molecule after absorbing the photon, and half mv square v2 square, and this is h into nu2. So according to law of conservation of energy, now we can write, that is we can show that half m v1 square is equal to half m v2 square. So since the velocity is negligible or change in velocity is negligible, so therefore these two things will be equal. So therefore we can write or rearrange it as E2 plus h into nu 2. I have taken this on the left hand side and this on the right hand side. So this is equal to E1 plus h into nu 1, or we can write E2 minus E1 is equal to h into nu 1 minus h into nu 2. So therefore E2 minus E1 divided by h can be written as nu 1 minus nu 2. H is common, so send it to the denominator. Now we can write nu 1 is equal to nu 2 plus E2 minus E1 divided by h, or nu 1 is equal to nu 2 plus delta nu. Okay, without writing directly, we can write it as delta E divided by h, and nu 1 is equal to nu 2. Now this can be written as delta nu. Okay, now let us see the different cases related to this. So what will be the different cases? Means if E1 is equal to E2, okay, then delta E is equal to 0, or delta nu is equal to 0. That is nu 1 is equal to nu 2. That is nu 1 is taken as the frequency of the incident light and nu 2 is taken as the frequency of the scattered light. So therefore if there is no change in the frequency, there is no change in the wavelength. So definitely this corresponds to the unmodified line or the original line. Now let us look into case 2, where if E2 is greater than E1, then what happens? Then nu 1 will be less than nu 2 and delta E will be positive. Now the molecule gains energy from the photon and jumps to the higher energy state E2. So therefore now delta E will be positive. So therefore we can write delta E is positive. So therefore nu 1 is equal to nu 2 plus delta E divided by h. Now we need nu 2, that is frequency of the scattered light. So therefore nu 2 can be written as nu 1 minus delta E divided by h. So therefore nu 2 is equal to nu 1 minus delta nu. So this will corresponds to the shorter wavelength. Why? Because nu 1 is the frequency of the incident light and nu 2 is the frequency of the scattered light. So therefore since nu 2 is equal to nu 1 minus delta nu, so this spectral line corresponds to the Stokes lines. So that is, if the frequency of the scattered light is less than that of the frequency of the incident light, then that corresponds to the Stokes lines. Now let us look into the last case, that is if E2 is less than E1, then the molecule loses some of the energy to the photon and jumps to a lower energy state such that delta E will be negative. Why? Because E2 is less than E1, so therefore delta E will be negative. So therefore the frequency corresponding to this particular spectral line can be written as nu 1 is equal to nu 2 minus delta E divided by h. Since we need E2, this can be written as nu 2 is equal to nu 1 plus delta E divided by h. Okay. Now we have delta nu is equal, nu 2 is equal to nu 1 plus delta nu. See, nu 2 is the frequency of the scattered light, nu 1 is the frequency of the incident light. Since we have nu 2 is equal to nu 1 plus delta nu, so certainly the frequency of the scattered light will be greater than the frequency of the incident light, where it corresponds to the anti-Stokes lines. Now let us see the applications of Raman lens, that is Raman effect. So where are this helpful for us? So Raman effect is used to study the structure of solids, liquids and gases. This is the first application, and the second application will be, it is used to study the nature of the liquids, and third application is, it is used to study the binding forces in crystals, and it is used to study the different rotational, vibrational, energy levels of a molecule. So these are the four applications. First application is to study the structure of solids, liquids and gases. Second application, it is used to study the nature of liquids. Third application, it is used to study the binding forces in crystals. And fourth application, it is used to study the rotational, vibrational energy levels of different molecules. Now let us see what are the characteristics of Raman lines, that is Stokes lines and anti-Stokes lines. See, the first characteristic is Stokes lines are more intense than anti-Stokes lines. If you calculate or if you find out the intensity of the Stokes lines, it will be having more intensity than that of the anti-Stokes lines. And in case of Raman lines, the Raman lines, that is Stokes lines and anti-Stokes lines, are symmetrically placed. What do you mean by symmetrically placed? Means if this is the spectrum, this is unmodified line, okay, and if this is the Stokes lines and this is the anti-Stokes lines, okay, so the distance between the unmodified line and this Stokes lines will be equal to the distance between these two lines. Okay, so this is said to be symmetrical. Okay, that is the Stokes lines and anti-Stokes lines will be symmetrically placed about the original line or the parent line, and they are strongly polarized. Raman lines are strongly polarized. It means that whenever you take the nickel prism and if you try to rotate in any direction, they show a plane polarization. So that is what we call it as, they are strongly polarized. And the next characteristics of the Raman lines is that the anti-Stokes lines, if the temperature is increased by somehow, that is if you increase the temperature, the intensity of spectral lines of anti-Stokes lines will increase. That is, if you increase the temperature of the substance by some means, the intensity of the anti-Stokes lines will goes on increases. So the next and the last characteristic is the frequency difference between the modified lines represent the frequency of the corresponding infrared absorption lines. Okay, so this is about the Raman spectrum, and by here we will be ending the first unit, that is atomic physics and molecular physics.